Hello, everyone. Back. Today we'll be talking about something called retrosynthetic analysis, which is a couple of fancy words, but they will make sense by the end of this lecture. And so the entire idea of this lecture is we are going to be focusing on a thing called synthesis, right? And synthesis is the most fun part of all of organic chemistry, because essentially what synthesis is you're using combinations of reactions that you've already learned to come up with ways to make new products. All right. And so essentially, you should be able to make almost anything you want given reactions in organic chemistry. So, thinking about this idea, I generated this reaction web for everyone previously, and I wanted to walk through how this works in terms of thinking about this retrosynthetic analysis and synthesis, just by giving you a rundown of how this reaction web works. Because essentially, if you take a look at this reaction web, it is very confusing, right? There's a lot of arrows everywhere, but we're going to make it very simple, very quickly. And so the way we're going to do that is we're going to ask ourselves the question, if we started out with this alkyne here, what would it take for us to get to the carboxylic acid shown here? Right? And so we're pretty much asking what steps do we have to take, which is what that question mark is for. What reactions do we have to take to get from one to the other? And so using this reaction web, we can get a pretty good idea because the first thing that we're going to do is we're going to define our starting point as alkynes, right? And the alkynes are down here in this bottom corner. So let's say the alkynes were where we start. All right. And then we need to find where the carboxylic acid functional group is. And so if you look through this, you'll start to get relatively familiar with it the more you look through it. But we see that right over here, this is where our end point is, right? Carboxylic acid. So the question becomes, how do we get from the start point, which is the alkyne, over to our end point, which is the carboxylic acid? And essentially what we're doing is we're using this scheme as a roadmap. Because no matter where you start, you should be able to follow some simple arrows to get from A to B. So let's start with our alkyne and think to ourselves, where can we go from here that will get us closer to a carboxylic acid? Well, when looking at this, we know the carboxylic acid is kind of diagonally upward, so we gotta want to start moving in that direction. And so we see that there's a couple arrows that are pointing away from our alkyne, right? We have this one here that points towards ketones, this one that points towards dihalides, this one that points towards aldehydes, and then there's this one right here that points all the way up to alkenes. So, thinking about these arrows, right? Because this other one points over towards alkanes, and that's probably not where we want to go because those are unfunctionalized. So, thinking about these other four arrows, the question is which ones are going to get us closer? Well, looking at this, we can say from the alkyne, going to the dihalide is generally not a good idea because once you're at this dihalide, the only direction you can go would be down this path, which just goes back to the alkyne. So essentially, this path is completely useless, right? Going to the dihalide is a bad choice. So we can just imagine that we're not going to do that. Now then, our other directions though, if we take a look at each of these, for the ketone, there is a direction we can go that's closer towards the carboxylic acid, right? We can go towards alcohols. So perhaps this is a route that is okay to take. The same can be said with the aldehyde, right? This can also be taken towards the alcohol, and so can the alkene. So looking at all three of these routes, essentially what we're saying is all of them can meet up at the same key intermediate, right? We would say the alcohol is relatively important because when we think about where the alcohol can go, it's one of the few groups that can be converted directly to the carboxylic acid. So theoretically, that would mean that all of these arrows go to the carboxylic acid. Except there is one minor thing that makes that not entirely true. If we take a look at what this says, it says CrO3, right, that chromic acid oxidation of a primary alcohol. And that is a very important statement. Because if we're thinking about primary alcohols, one of these groups is not compatible with what we just said, and that would be the ketone, right? A ketone, when converted, is going to make a secondary alcohol because it already has these two carbon groups hanging off of it. So if this makes a secondary, that tells us that this is actually not a reliable way to get to the carboxylic acid. But these other two routes make sense, right? The aldehyde does generate a primary alcohol, and then the alkene, we can make a primary alcohol. So let's think about how we would use these in terms of going through this reaction scheme. So let's first go via the aldehyde route. And if we're thinking about going aldehyde, first step is first to make the aldehyde from the aldehyde. So this is the aldehyde that we've been given, and we want to make it into an aldehyde. How would we do that? Well, we would say that the best way to go through and make this into the aldehyde would be through going down the route of a hydroboration oxidation. Because if you remember, after adding in the BH3 and the NaOH and H2O2, this does an anti-Markovnikov addition of the alcohol, which makes the enol, which then tautomerizes to form the carbonyl, which in this case is the aldehyde. So that is what that says right there. Hydroboration oxidation will get you to the aldehyde. From here, it says reduction or Grignard. Now, if we're thinking about a reduction or a Grignard, in this case from the aldehyde to the alcohol, we have to think about which one of those makes more sense. And to do that, we need to look at this product, right? The product in this case has a carboxylic acid, and it's not like there's any other carbons added, which means that if we're thinking about our aldehyde, we also don't want to add any carbons. We can instead just go right on through and do a reduction. So in this case, we can do something like sodium borohydride and methanol, right? And once we do this, we should have our alcohol. Now then, looking at the alcohol on our reaction web, to take it to a carboxylic acid, we have to do a chromium oxidation to the carboxylic acid. And so that would just be taking CrO3, and remember that the reagents with this are H2SO4 and water. And this, of course, takes the primary alcohol, oxidizes it into the carboxylic acid. So this would be one successful way to make that carboxylic acid from the alkyne, right? And to get there, all we had to do was use these simple steps in the road to get from A to B. Now then, there were another direction we could take that was also reasonable, going through the alkene. So let's think about what it would be if we went via the alkene. Well, in the case of the alkene, step one would have to be, of course, converting our alkyne into an alkene. And to do that, we have multiple methods, but I'm going to do Lindlar's catalyst because remember, in this case, it doesn't matter which alkene we form because it's monosubstituted anyway, so it can't be E or Z. Now, from here, getting to the alcohol from this alkene has multiple paths, right? We can do hydration, oxymercuration, or hydroboration, right? And these three are all technically different reactions. And thinking about what they do, if we tried to do something like a hydration, right, using H2SO4 and H2O, what we'd end up doing is we would form a carbocation, and then we would attack it with water, and that would end up giving us a secondary alcohol, right? And we know that this secondary alcohol is not good for us because essentially oxidation of that is going to make a ketone and not a carboxylic acid. On the other hand, if we tried something like hydroboration, right, using BH3 and then sodium hydroxide with H2O2, we immediately convert into the alcohol. From here, it's the exact same idea as what we saw via the aldehyde route. Taking this, using H2SO4, water, and that CrO3 as our oxidant, and that gives us the carboxylic acid. Right? So no matter what we're doing, we can use this roadmap to give us an idea of how to convert between those functional groups. That being said, on this roadmap, you'll notice that all of the reactions here are just listed as the names and not the actual reagents. So you do need to know the different reagents in order to figure this out. Okay? So that's something to keep in mind about all of these. But essentially, if you want to use this as a practice piece, what I would suggest is look at this worksheet and just choose two different spots on it. So let's say that I chose to start at an anhydride and I said, let's try and end at an epoxide, right? The question becomes, how do you get there? And a good thing that you can do to practice your skills on these reactions is to go through and figure out exactly how you would get from A to B. All right, I would recommend taking the time to do that and just putting these into some random generator, pulling out two groups and trying to find the path that gets you from one to the other. Because, for example, from the anhydride to the epoxide, you could go through this nucleophilic acyl substitution, then a reduction to get to the alcohol, and then an intramolecular SN2 to get to the epoxide. But that being said, you have to think about this, right? Would the intramolecular SN2 make sense? Well, no, because you would also need a leaving group. So the question then becomes, well, is there a better way to do it? Yeah, there is. You could instead go through the alkene and then to the epoxide. So all of these things should have a path to get from A to B, but make sure that you reason through and think about what makes the most sense given what you have. Now then, one of the other things that we can do whenever we're looking at these synthetic problems is we can ask ourselves not the question of how can I go from the starting material to the product, but rather thinking about if I look at the product, what are some features of that that I can use to elucidate what the intermediates would be that come before it and how those relate to the starting material. And it's a little more complicated to originally think about it this way, but it helps a lot. And this is a process that we call retrosynthesis or retrosynthetic analysis. And the entire purpose of retrosynthesis is you use the product and work backwards to find out what intermediates make the most sense. And for this type of problem, it's going to seem very similar to the synthetic approach, instead of doing this retrosynthetically. But we're going to do it this way, and then we're going to use an example that actually proves how retrosynthesis can be a little bit more useful, right? So if we think about it in this case, right, what we'll do is we will start out by drawing our product, right? And so this will be our retrosynthetic analysis. Now what we're going to do is we are going to use these types of arrows here, and these are called retrosynthesis arrows. And what they're basically showing is what is on the left can come from what is on the right. So it's essentially taking the idea of these reactions and turning it in the opposite direction. So, using the retrosynthetic approach, making carboxylic acids gives us a lot less approaches than we had before with the alkyne. Because with the alkyne, we had multiple directions that made a lot of sense to go. But this time, if we look at the carboxylic acid as our endpoint, and we think about all of the things that surround it, we can actually narrow it down really quickly. Because if we look over towards the acyl halide, it doesn't make sense to make this into an acyl halide. That gets us nowhere near closer to the alkyne because the acyl halide just does a bunch of nucleophilic acyl substitutions. Same with the anhydride. It doesn't make any sense to go in that direction. And also same with the ester. None of those actually get us closer. The only one that does is towards the alcohol. So that immediately tells us that, hey, if we want to do this, we are going to have to make this alcohol. And if we're thinking about this alcohol from the alkyne, we can say that, well, to get here, the best way is to go through the alkene. But the good thing about doing it this way, in comparison to what we saw up here, is we don't have to debate between the different types of reactions that the alkene can do. Instead, we already know that the alcohol has to be on this position here. And we can just say, okay, if it's coming from an alkene, it's going to end up on that position. And then from there, we can say to get to an alkene, it's very simple from the alkyne, right? So working backwards is sometimes easier than working forwards. But in this scenario, it may have seemed very similar. Now, once you've done this, you do then have to take this and figure out the reagents for each step along the way. But keep in mind that this is a good way to figure out what each of your intermediates are. Because essentially, once you know the intermediates, right, because we now know what these are, the intermediates help us move forward. So, this may not seem super useful in this type of scenario, but in this next one, it's going to seem quite a bit more useful. So let's do another example of a synthesis. But let's say for this one, we're going to start from this alkene, and we're going to do some number of reactions that will get us to this alcohol here. So, in this case, if you were just trying to go from an alkene to an alcohol, it's not that hard, right? All you'd have to do is a hydration, oxymercuration, or hydroboration, one of those. But the one thing you'll notice about this synthesis that's different from the ones that we just looked at is the starting material has 3 carbons, but then the product has 5 carbons. So essentially what we're seeing is somehow we are adding carbons, which has to be done through specific reactions, right? So what are those specific reactions? Because this is a very big hint for us. Well, if we think about forming CC bonds, right, they are formed via Grignard or alkyne SN2. So, using this idea, there's actually a lot that we can do to think about what would be the best way to do this retrosynthetically, right? Because if we're going to do a retrosynthesis of this, there's a lot less options for what we have to try. Because with the starting material alkene, there are many ways that you can go to get ready to make a Grignard or to get ready to make an alkyne, do SN2, all that good stuff. Instead, with the retrosynthesis, to make the alcohol from something that's useful, let's just say we're going to start by thinking about doing an alkyne SN2, right? If we're doing an alkyne SN2, we're essentially saying that at some point, this is going to have to contain an alkyne, which is very useful to us because thinking about this containing an alkyne, we know that we can work backwards from the alcohol to get to an alkene, right? Because alkenes can make alcohols. And even more so, alkynes can make alkenes, right? And so using retrosynthesis, we were actually able to get to this as the important intermediate, which would be really hard to see from the starting material that we had there. So knowing that this is an important intermediate, now we just have to ask, how do we get it on there? Well, clearly, if we're going to be adding on 2 carbons, they're most likely going to be this carbon and this carbon. And this is where that idea of alkyne SN2 comes in, because I see a primary carbon right here that we could substitute onto. So if that's the case, if we think about doing an SN2 there, we would have to have an alkyl halide as well as this acetylide that we would use as the nucleophile upon deprotonation. Now, that being said, it's a good idea for us to look back at our starting material at this point because we see that we have that alkene at the start, and we see that in our current intermediate, we have an alkyl bromide that can easily be made from said alkene. So retrosynthetically, we got from here to here. And to be fair, there were other directions we could have gone with this. All right, we'll talk about using Grignards in a second, but we could have even went a different direction where instead of making the alkene, we could have had the ketone instead, which would have been very easy to synthesize from an alkyne. So usually during synthesis, multiple paths are possible. The only thing is, you just need to figure out what makes the most sense to you. Now, once we've done our retrosynthetic analysis, we do need to go through and do the forward synthesis, right? So we need to plug in all of the reagents that we would use to actually do this synthesis. So starting from the alkene, if we want to get to that alkyl bromide, we would have to add it anti-Markovnikov. To do that, we know we can use HBr with H2O2, right? That is the radical reaction that gives us the anti-Markovnikov addition of the bromide. Now then, what we said we were going to do is an SN2 that uses this acetylide with that alkyl bromide. But keep in mind, this is not a strong nucleophile at the moment. Instead, what we need to do is we need to add some type of base. So we can add some NaNH2, and that will deprotonate the alkyne so it can do the substitution, giving us our now higher carbon count. From here, we now need to make it into either an alkene or the ketone. So what we're going to do is we're going to just do the alkene at the moment. So the easy way to make alkenes from alkynes, H2 and Lindlar's catalyst, right? So there's that hydrogenation. That takes us down to the alkene. And then from there, we need a Markovnikov addition of the alcohol. And a good way to do that would be a oxymercuration, right? So that would use our mercury diacetate with water and then finish it up with the reduction using sodium borohydride. Now, keep in mind, you could have also done that through a hydration reaction. Both are perfectly fine. But in either case, they'll get you to the same product. Now then, like I said, there are already two paths shown in our retrosynthesis here, but we did mainly focus on this idea of alkyne SN2 for this path, right? What about Grignards? Well, this is another very simple way that we can actually do these reactions. And so if we're thinking about doing a Grignard reaction, this takes a little more skill in terms of thinking backwards at what has to come from the other thing, which is why I brought up the alkyne addition first. It's actually a lot more easy to see in the long run. Because if we think about a Grignard reaction to form this alcohol, right? Because if you think about a Grignard, we're adding something into the carbonyl and then we are protonating the oxygen to make it an alcohol. There's actually two different Grignards that we could do. The first one would be if we use the left side as our Grignard reagent, right? So there's our magnesium bromide, and then we have this as the carbonyl that we're adding into, right? Because if we count our carbons, there's 1, 2, 3, 4, and 5. And so that would be as if we were forming the bond here in blue, right? But we could also do forming the bond here in orange, right? So we'll call this the blue bond, and the one down here, the orange bond. Right? If we formed the orange bond, That means our carbonyl would be this here, and then we would use methyl magnesium bromide as our Grignard reagent. And so both of these routes are viable, but the thing is, only one of them makes more sense. If we look at this top material here with the Grignard, right, this has 3 carbons. Our starting material has 3 carbons. So this looks more like the starting material, right? The bottom one, we're looking at something with 4 carbons and 1 carbon, and neither of those match up to the starting material, so it's going to be a little difficult to use the starting material to get to there. So essentially, it makes more sense for us to go with what we see up top with the blue bond, and then just forget about trying to make the orange bond. So if we want to take that methyl magnesium bromide and make it, remember that all Grignard reagents are made from the corresponding alkyl bromide, right? And it just undergoes that reaction with magnesium. And from here, we know the very simple conversion to the alkene. So this is another example where these last two intermediates are the exact same as what we saw up top. And that is what makes it a little harder to do this synthetically, thinking from the starting material forward, because there's so many different routes that you can take. So, looking at this, now we need to do it in the forward direction. Right? So our synthesis would consist of taking the alkene, hydrobromic acid with H2O2 will give you the anti-Markovnikov addition of the bromide. From here, if we want to make that into a Grignard reagent, we use magnesium metal and do that insertion that we talked about during the alkenes chapter. And then from here, it is a very simple addition to the carbonyl that we already had written out up here, right? So it's that 2 carbon aldehyde, right? And we can use THF as a solvent. And then the second step of that reaction there is that we would have to add in H2O with HCl, right? Because upon adding in, we'll have the anion on the oxygen, and we need to protonate that in order to make it the alcohol. So this would be the synthetic method that you could use to make the product using this Grignard route. So essentially, when we're thinking about synthesis, there were at least 3 routes that we could have taken to get to the final product based on what we started with. And so usually synthesis has multiple paths. So you personally can figure out what makes the most sense to you. For example, if it was very easy for you to see where the Grignard reaction was coming in, you could take that path. If it was a lot easier for you to see the alkyne reaction, you can take that path. Now, that being said, there are incorrect ways to do synthesis, right? We had already presented up top some ways that you could accidentally make the ketone, and then that's not going to oxidize to make what you want. So the reactions still have to do what you need them to do. It's just overall, since there's many available paths, if one makes more sense to you, it's going to be a little easier to see that path. So we're just going to go through a couple more examples, and then I'm going to give a list of syntheses that we're going to do in the next lecture, because this is really the main final point that we're going to be going through is just how to do synthesis, how to think about synthesis, and then just looking at how to combine our reactions to make the stuff that we want. So let's do this next example. And this one is going to be a little different from the other two because we're going to add in some stereochemistry. So it's going to be this plus its enantiomer. And the one thing that you'll notice about this is that stereochemistry is actually very useful in these because essentially when you look at stereochemistry, I'll do this in a different color. It gives you a hint, right? Essentially, what it says is you're using a stereospecific reaction, right? And so, if you think about this in terms of what type of stereoselective reactions you're going to see, there's quite a few in alkenes as well as SN2, but it actually eliminates a lot of things that we can do. The other thing you'll notice about this example is the starting material has 4 carbons, the product has 6 carbons. So we're adding carbons once again. So let's actually just work backwards and think about what reaction would give us that specific stereochemistry. Right? Whenever I look at the alcohol and the bromide, I think to myself, they're anti. Do we know a reaction that gives us an anti-alcohol and bromine? Well, yes, we do actually. From an alkene, we can do that because the alkene can be put through a halohydrin formation to give us that type of stereochemistry. And now looking at this alkene, it's kind of becoming more obvious to me that, oh, hey, these 2 carbons over here that I'll label in blue could be added on through something like an alkene or an alkyne SN2. So if we want to do an alkyne SN2, that means that this alkene would have come from an alkyne. And then from there, that tells us that, oh, hey, we must have done an SN2 to add on these 2 carbons. And just by doing that, we have found ourselves at the starting material, right? That 4 carbon containing alkyne. So now all we have to do is work ourselves from that alkyne to the final product using our actual reactions. So how do we do this? Well, to do this alkyne SN2, we would need a base to deprotonate the alkyne, and then we would need something to substitute onto, such as this primary alkyl halide. That is going to go ahead and give us that intermediate that we saw, which we can then make into the alkene. And keep in mind, when we're doing this, we do have to follow some stereospecific rules for this alkene, right? I drew it as the E alkene because the E alkene is the only one that's going to give us that stereochemistry and that orientation. So when we do a reaction with this alkyne, we also need to make the E alkene beforehand. So in this case, we need to do a dissolving metal reduction rather than the Lindlar's catalyst that we've been using previously. Because in this case, it's going to end up generating the E alkene instead of what we would see with Lindlar's, which would be the Z. Now from here, we can put it through a halohydrin formation using bromine and water in order to give us the final product, which is that anti-addition of the water and bromine, and of course it generates the enantiomer as well. So essentially, using these ideas of stereochemistry giving us hints, adding carbons, and different functional groups, we can come up with a better idea of what reactions we need to do to get from A to B. So with that being said, let's do one more example before I give us the list of different syntheses that we need to try for the next lecture. So for this one, it's going to be a little different. We're going to start from this, do something, and generate 2 of these molecules. So this one's different from the others because we started out with something that had all of these carbons, and now we end up with 2 different products with less carbons. And whenever you see something like this, essentially, this right here is a major hint, right? Because what we're saying is we're cutting the molecule apart. And think about that. What reactions do we know that cuts the molecule in half? Ozonolysis is the only one. And that immediately brings us to a useful intermediate, right? So this is a mixture of synthesis and retrosynthesis already. Because what I'm saying is, if we need to cut this molecule into something that has these four different carbons and then the oxygen with the methyl, we're going to have to cut it in half down that bond right there. And if we cut down that bond through an ozonolysis, we would essentially have to make two of this carbonyl. So the question is, what does that come from? Well, that comes from what would be the alkene there, right? Hopefully you can see that alkene being cut would generate those carbonyls. And of course, that alkene could be easily made from the starting material that we have, right? Through an E1 reaction. And so this has already given us part of the mystery solved, right? We've gotten to this intermediate here, but it doesn't get us all the way to the very end. Now we need to ask ourselves, given this, we can technically think of this as like the new starting material, right? Knowing this, what can we do to work back to it? Well, essentially, if we want to get to the oxygen with the methyl group, the way I see it, we would have to do some type of SN2 to get that methyl group on there. And so SN2 would have to have an alcohol as the nucleophile, and then something like methyl bromide as the electrophile. And of course, when we look at this compared to our carbonyl, we see that it's not very hard to get from carbonyl to an alcohol. So this would be the whole retrosynthesis here, right? We used the information from the problem of cutting it in half to figure out a reaction's going to happen somewhere in the middle of the synthesis, and that allowed us to build from those two sides. Because looking at this starting material, it's not immediately obvious how all of those carbons and that oxygen come into play. So now we just have to provide the actual synthesis for this. Well, like I said, from the beginning, we can take this alcohol and we can do an E1 reaction. And as a reminder, how we do this would be through H2SO4 and heat, right? Because the H2SO4 can protonate the alcohol, make it a better leaving group, and then the heat helps you do an E1 reaction. Okay. From here, we want to do ozonolysis. So we're going to use ozone along with dimethyl sulfide, and that's going to cut the molecule in half to give us those two carbonyls. Now then, from here, we need to do a reduction. In this case, we can once again use sodium borohydride and methanol, and that will generate our alcohol. And then from there, we see that we just need to do the SN2. So to do that, we would need a base to make this oxygen a better nucleophile, right? Because we are going to be adding in methyl bromide, which is practically a primary leaving group. And so if we use something like sodium hydride, that'll deprotonate the alcohol, make it a strong nucleophile so it can do the SN2. And that is what will give us our two ethers as the final product. Now then, all of this synthesis knowledge is stuff that you have learned throughout the course. But the thing is, you need to be confident in it. And so when we're looking at all these reactions, and I'm stating what each reaction can do, it all relates back to the fact that I'm very well aware of how all these functional groups interact in these types of reactions, right? Whenever I was thinking about this last problem and looking at the final product being an ether, from my mind, right, the ether as the final functional group would have to come from the one of the two things that make ethers are either alkenes or SN1 or SN2. But of course, it was easier to get to the alcohol with the alkyl halide as the intermediate. And so all of these three things combined get us to the ether, which you would know if you were able to really recognize what each reaction is doing. So everything from this lecture is based on the fact that you need to understand how these reactions play together to make different functional groups and what those functional groups can do. All right. So I highly recommend using this roadmap as a tool to go ahead and figure out exactly how every functional group is related, how you can use specific functional groups to make specific things, so on and so forth. Now then, that being said, I did promise that here at the end, we're going to get a list of syntheses for you to try. Okay? And I want you to take these syntheses and try on your own. All right? Because these are going to be useful in developing your skills on the, I guess, web we just saw. And it's going to assist you in really taking everything and bringing it together for this course. So, that being said, questions like this are also possible on the ACS, just saying what reagents would accomplish this goal, and it'll give you A, B, C, D with different things attached to it. So, looking at this, right, for this first reaction, all right, we're going to look at going from this alkene here to this diol with specific stereochemistry. With its enantiomer. All right, so a couple hints are already dropped there. Now, I will say for each of these syntheses that I'm going to put up for you to try on your own, I won't tell you how long they are. They can range anywhere from 2 reactions to many, many more. But just keep in mind that it doesn't matter how many reactions it takes you to get there, as long as the reactions make sense and they work together to make what you want. So, for the second one, we're going to start from an alkyl bromide and say, what reactions do you need to do to get to this interesting structure with 2 aromatic rings and an alkene? For the third one, starting from an alkyne and getting to this product with an alcohol and a big old aromatic ring attached to a carbon. Fourth one is going to be a slightly tricky one. I will say this one is one that you think would be easy, but it's a little more difficult. It's going from a trans or a E alkene to a Z alkene. For this fifth one, this one is also tricky. But you can do it if you do your retrosynthetic analysis. The sixth one is going from an alkyne to an alcohol. This one is a little bit easier, so you may want to start with that one if you're having some trouble. For the seventh one, going from this aromatic ring with that alkyl chain off of it to an epoxide. Then we also have this one here, which will be starting from this alkyl halide and making this carbonyl here. Number 9 will be going from this alkyne to this alcohol. And then number 10, the final one, will be going from this here. Oh, sorry, I need to, these look a little nicer. To this product right here. So for this last one, I will tell you, it is difficult. So I'll give you the number of steps it should take. It is 5. And so all of these different reactions, The answers and thought process will be discussed in lecture 38. But until then, I will give you just a relative, I guess, easy to hard idea for each of these. So we'll say green is relatively easy and red is very hard. So like I said, number 6, number 7, I would say are very easy. I would say that number 8 is relatively medium. Um, I would say number 9 is relatively easy. Number 10 is definitely hard. Looking back towards these other ones, number 5 I would also say is hard. Number 4 I would say is pretty medium. Number 3 I would probably classify as hard. And then number 1 and 2 are both relatively medium in terms of difficulty. So use those to judge when you want to try each of these in terms of their order. And then we will present those during lecture 38. So until then, try all of these. Have a good Thanksgiving break, and I will see you next time.